seen this aspect of it, like the application, but not in this setting, because this is actually how you do it. So basically the idea is this. Okay, so you have all this data, right? Good. And you'd like to find trends of the data. What's a good way to, I don't know, say, plot an equation that could possibly give you future values? Well, I mean, you could plot the line going like this. Oops. Right? I mean, that one looks kind of okay, right? But I mean, there's lots of other lines you can plot. I mean, this isn't the only one. So the question that becomes, so the question is which out of the million of lines that you can choose is the best one, right? So choose is the best one. Well, what is the best one in this case? Well, the best one would be the one that basically, if you take every point on here, right, and measure the distance from the point to the line, the best line would be the one that has minimizes that distance between every line, every point, sorry, right? So, I mean, you wouldn't want a line that's like over here, right? Because then the distance from those top points would be very big, right? You want one where the, I guess you can say the average of the distance of every point to the line is as small as possible, right? So that would be the best line in that, I guess, scenario. However, we can formulate it in a much better way, and that way is this way. So for, let's just say example, let us say we have the data points, say 1, 0, 2, 1, and 3, 3, right? So how can we want a line, say y is equal to c1 plus c2 x, that best fits it, right? Fits, I guess you can say, the point. Here's 1, here's 1. So here's 1 point right here. Here's 2. So here's another point right here. And then 2 and 3. So here's another point up here. So we want the line that best fits it, meaning it's like something like this, right? Okay, well, how can we even attempt to do this? Well, and maybe in college algebra we would have seen that if they just give you 1 point, you can literally just find, or 2 points, you can find the C1 and C2. So one way you could, I mean, the naive way to do it initially is to just plug in those points, the points, into, I guess, let me call it star, right? So x is 1, plug in x, y is 0. So the first equation you'd get would be c1 plus c2 is equal to 0. Plug in the other one. The second one, you get c1 plus 2c2 is equal to 1. And then the third one, you get c1 plus 3c2 is equal to 3, right? Basically, what you want to do is then solve for your c1 and c2 in this case, right? However, there's like lots of solutions to this. So, I mean, we can pick many values for C1 and C2 that would satisfy well, actually no, I take that back. This one, if you I guess translate it to I guess a matrix equation, right? We get A is equal to what? Well, A is going to be 1, 1, 1, 2, 1, 3. X is going to equal to C1, C2, and B is going to equal to 0, 1, 3, right? I mean, that's what we always done, right? Now, if you try to actually like solve this with RREF, you'll more likely find that this is an inconsistent system. So there is no solution to this. However, that won't stop us from finding the best line, okay? So just by the way, if there was a solution, what would that mean in regards to the line? I mean, it means that there's one line that literally like crosses all 3 points. So the best fit line would be the one that like goes through all 3 points, right? But since this one we're saying that it doesn't go through all 3 points, we're just trying to find the best fit. Obviously, this isn't going to have a solution. So what we can do then is do this. So this equation, I guess we can say AX equals B is inconsistent. Instead, so what we can do is then do, okay, well, consider AX minus B, right? Okay. So obviously, if it was consistent, then AX minus B would be 0. However, since it's not consistent, we want to minimize the distance between AX and B. So we want to take the min of this basically over every vector in, I guess, Rn. So the question that becomes, how do we minimize AX minus B? Because if we can minimize that, then that's the best fit line in that. Then if we can find such a X, then this will be the best fit line. Okay. So okay, perfect. Well, that's great and all. Yes, this is all true. However, how would we ever hope to check every single vector in Rn, which there's, by the way, an uncountable many of them, to see which one gives you the minimum, right? How do we even proceed to do this? Well, it's a good thing that we have. Well, we've learned a lot of things about vector spaces, orthogonal spaces, and basically we're going to use all that to show you what the equations that we need to solve for will minimize this AX minus B. So first of all, we need a few things. So those few things, I'll go through it, but basically the idea is going to be this, okay? So pictorially, we have, okay, so basically, if you take the column space of A, right? Or rather, yeah, I guess you can say the span of A. Yeah. So if we have something like, let me see, how do they draw it here? The column space of A, which we'll call S. So we have this plane, right? And this plane is, we'll call S. So, by the way, what is the column space of a matrix again? Is the span of all the column vectors in A, right? So I mean, if A had like A1, A2, AN, then just take the span of it. So it's all possible linear combinations of the columns of A, which by the way is again what? All possible, it's basically all possible solutions to the equation AX equals B, right? So the vector B that we're trying to find isn't going to be in here, but we're going to try to minimize the distance between. So basically, if you had these the equation AX equals B, right? The column space of A is going to contain B. B is going to be in this plane right here. However, if it's not, then I mean, ours is going to probably like point upwards like this, something like that. So all the solutions to AX equals B is in this plane, right? But if it's not, then it's going to not, be in the plane. It's going to probably like go out of it, okay? So this is the first observation, pictorially, okay? So again, this is like, this stuff in here is like A times X, okay? Every possible A times X is that plane in this case R3, right? Okay. The next thing is, okay, well, I would like to minimize, if I want to minimize the distance between this vector right here and that plane, well, wouldn't it just stand to reason that all I have to do is just like look downward right here? Like just literally just look down exactly where it's at, and then look at this, and so this distance right here is the minimum between that plane and that arrow and that vector, right? Wouldn't you agree? I mean, if I told you here, okay, what's the minimum distance from this point to that plane? Well, you're not gonna go all the way over here, right? You're gonna go straight down to it, right? That's exactly what we're trying to do here. So that's what it is. This is what we're trying to do with the picture, okay? We're trying to find that distance. Right? Okay, perfect. So now we have the idea in picture. Well, okay, so now the next question would be then, what is this vector right here? That vector that's pointing to that point that's like right below the blue, the red arrow, which I should probably count as B. So that's B. Didn't we do something like similar to this already? Maybe not with planes, but with other vectors we have. So what's happening here? So what is the green arrow in relation to B? It is the projection of B onto that plane, right? So remember, if you were to project a arrow B, this vector B onto this vector, I guess a B here, all you have to do is drop down, and then this vector right here is the projection, right? Same thing, it's just that now this is a plane, okay? So we need to develop the ideas of what it means to project a vector onto a subspace, okay? So two things we need. We need to know projections onto subspaces. And then the other thing we need to know is orthogonal complements. Because as soon as, okay, but remember, what are we trying to do? We're trying to find the vector that minimizes the distance between. So we're trying to find this red vector. This is what we're trying to find. Sorry, hold on. Sorry, no, not the red one. We're trying to find this vector, x, right? that minimizes the distance between the red vector and that plane. So remember, this thing can be a vector. These things are vectors in there. They can just be in any direction. So out of those millions of vectors in that plane, we're trying to find the green one, basically, right here. This green one right here, which is going to end up being this x. Okay. 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 So now we have the idea. Let's develop the tools, which is going to be very fast. And don't worry, after I develop the tools, you can decide to forget it all and just use the equations I give you at the end, and then that's it, basically. All right. So let's see. So let's define something. Let's say we have let S1 and S2 be subspaces of the vector space Rn. Okay. Then S1 is orthogonal to S2 if v1 dot v2 is equal to 0 for every v1 in S1 and v2 in S2. Okay, so it just means that literally the planes are like perpendicular to each other. Okay, so this is what it means to be for two subspaces to be orthogonal. It means that every single vector in that subspace is orthogonal to every other vector in the other subspace. Okay. The next thing we need to define is orthogonal complement. So the next thing is this. Let S be a subspace of Rn. The orthogonal complement of S is the set is the subspace. Well, hold on. Let me think it's a subspace. Let me just be sure to just say set, so I don't say anything. So it's a set is denoted like this, and it's defined to be the set of all vectors B in Rn, such that B dot U is equal to 0 for every U in S. All right, so take a subspace, make a set out of all the vectors that's orthogonal to every vector in that subspace, and that's the orthogonal complement. All right, so okay, so how do you find the orthogonal complement of a? So now the question is, how do we find the orthogonal complement of a subspace? And the answer is basically this. So if you have a subspace and you have its basis, right? Take that basis, make it into a matrix, take its transpose, and solve for the null space of it. Okay. So all this is coming back, right? So the answer is this. Form a matrix out of the basis of A or of S, and then also maybe just add this right here, matrix A, and then solve for A transpose times, I guess, x is equal to 0. And if you solve for the solutions of this, that whatever comes out of that, if you take the null space, right, the space of all vectors such that it satisfies this equation, this thing is the null space. Okay, I mean this thing is the orthogonal complement. So example, find the orthogonal complement of, say, S is equal to the span of all these vectors 1, 2, 1, 0, 0, 0, 0, 1. Okay. So solution, according to what I just said, make a matrix A, which is going to consist of those vectors right there, 1, 2, 1, 0, 0, 0, 0, 1, right? Then solve for A transpose X is equal to 0. In other words, 1, 2, 1, 0, 0, 0, 0, 1 times x1, x2, x3, x4 is equal to 0, 0. Okay. If you solve for this, let's see. Well. So. Okay, so let's see. I guess if we solve for this, yeah. So solving, get x1, x2, x3, x4, right? And let me put this over here. Okay, so this will give me that x1 is equal to minus 2x2 minus x3, and then x4 is equal to 0, right? So our solution is x1, x2, x3, x4 is going to be equal to, well, minus 2x2 minus x3, x2, x3. So here you can see x2 is free, x3 is free, and then 0. If you do this, then you get x2 is equal to minus 2, 1, 0, 0 plus x3 minus 1, 0, 1, 0. So this stuff right here, take the span of that. So then orthogonal complement is going to equal to the span of those vectors right there. Negative 2, 1, 0, 0. Negative 1, 0, 1, 0. Okay. So this is, yeah, for sure. Yeah. So this is how you take the orthogonal complement, find the orthogonal complement. So in other words, S complement is the null space of A transpose, right? And we're gonna basically use this effect in order to answer the question that we had previously. Oh, which part? Right here? Or okay, yeah, so I basically just split up the so basically from here, I guess you can say if I do so resize, I just split them up basically. I split up everything to have just so minus x2, 0, 0, minus x3, 0, x3, 0. You see how I just split up the vectors? And then after that, I just factor out an x2 and an x3, and it gave me that. It gave me this very next step. Okay, so let me go back because someone else was trying to like get this. Yes, okay. Okay. 167. Okay, so next thing we're going to talk about is something called a direct sum. It's just some properties that we should know about just the whole for vector spaces in general. But after that, basically, I'm just going to go into what it means to project a vector onto a subspace. And then once I do that, I'll basically just tell you, okay, so now we have the tools we need in order to answer our question, right? All right. So I guess remark. The complement of S is equal to null, or the null space, I guess I'll just note it like this, of A transpose, where where the original A columns are the basis of the subspace S, okay? That's basically what we just had right now, right? That was what we just had. Okay, next thing. Definition. Let S1, S2 be subspaces of, let's say, R. So let's see. How can I do the direct sum of S1 and S2 is denoted like S1, and then this is the direct sum with this like circle with a plus sign. If every vector can, and I guess every vector in Rn can be written as the sum of a vector, little s1 and s1, and little vector s2 and s2. In other words, so i.e. for every x in Rn, there exists a unique way to write S2 and S2 such that x is equal to S1 plus S2. Okay? Basically, that's literally all it means. Is if I pick a vector in Rn, and if I can write it as a vector in the subspace S1 plus this vector in the subspace S2 uniquely, then S1 direct sum S2, which is this thing, is basically this thing is basically the set of all, you can think of it as the set of all S1 plus S2 such that S1 comes from S1 and S2 comes from S2. That's literally all it all means. Now, the direct sum here is informal because really it's not what this is. It only works at finite dimensional vector spaces. If it was infinite dimensional, then all bets are off basically at that point. You have to use the actual definition of it, which is very ugly, and I don't. And that's way beyond the scope of this class. As is also the tensor product between two vector spaces. Okay. Basically, the reason I wanted to show you this is because Rn can be written, well, any vector space, really. If you have a finite dimensional vector space, you take a subspace of it, right? take its orthogonal complement, direct sum both of them, that direct sum should give you the entire vector space again. So this is what I mean. So let's see, let's just make this a little bit more smaller so I can so theorem, or rather, let me just go to the next page. So theorem 5.4.1. Let S be a subspace in Rn, then the following are true. The dimension of S plus the dimension of the orthogonal complement is just going to equal n. 2. The direct sum between S and its orthogonal complement is just going to be Rn. And then 3, the orthogonal complement of the orthogonal complement just gives you back S. Okay? And then finally, the one that we've needed is this. If, let's say, U1 through, I guess, you say T is a orthonormal basis for S, which is a subspace of Rn, and B is an Rn, then how you project B onto S is basically you take the sum from n equal 1 to, say, T of B dot U of N U of N. Okay. So it's almost like the Gram-Schmidt process, but anyway, this is how you project it onto it. All right. So you remember that green vector that I was trying to get on that projection over here. So I'll go back to it right now. But so if you remember the plane I had, right, the column space of A. This one right here. This green, this thing right here, right? This thing is basically projection of B onto S, or rather projection of AX onto B. But so that's the green arrow. So now we basically got what we needed. So this thing right here is that. Okay. By the way, if you guys are just completely lost, don't worry. Dimension. So the dim is the dimension of the subspace. So remember, the dimension is what again? I have to keep telling you because so the ones I keep repeating, by the way, are the things I will say on the test, just FYI. So what's the dimension? How do you find it? Yeah, number of bases, yes. Okay, so what was it? Oh yeah, by the way, if you guys are completely lost, don't worry about it. At the end, all this is just going up to some equations we're gonna use, and you just use those, and just don't worry about all this other stuff. This is I'm just building up the theory that leads to it. Okay, just for you guys to see that all that mumbo jumbo stuff that we talked about isn't useless, basically. All right. Okay, so. What much time I have this? Okay, so I think we have enough to basically do this. Okay. Okay, Okay, so let's not use an example yet. Let's just use, yeah, let's use the example of least square problems. Yeah. Okay. So going back to our original problem. We have this, so remember, we had a plane, right? Or how do I draw this right now? So we had this plane, right? We had this red vector coming out of it, and we call this vector B. Our problem was to find this green vector here that basically is like straight down, right? So because it goes straight down, this is a 90-degree angle, by the way. So now you can kind of see where we're going to use orthogonal stuff. Well, what is this green one right here? Well, again, this green one is just me projecting B onto this plane. So this is going to be the projection of B onto S if this big plane is S, right? This subspace S. And what is this over here? That guy would be B minus the projection of S, of B onto S, right? Okay. We're almost there. And now all we have to do is translate it to our problem, which is this. Okay. Let's see. Sorry, hold on. Let me just think about it. If I can say this properly. So S is, again, the subspace is so we have a matrix A. S is going to just be the column space of A, right? In other words, this vector here, it's going to be A times X. For that particular X we're trying to find, okay? Okay, so right, so we're trying to minimize again. So again, we are trying to find X such that AX minus B is minimized, right? So I mean, this blue line right here is exactly well, it's exactly AX minus B, by the way. If you just, I mean, well, I guess in this case it would be if you do it that order, it would be B minus AX, right? So what is this? Okay, so the thing we need to know is this. Do you agree that this blue line is orthogonal to that plane? Meaning it makes a 90-degree angle. I mean, if you drop it straight down, if you drop a line straight down from the red vector, isn't that making? I mean, it's right here, right? It makes this right triangle, right? So the blue line is definitely 90 degrees to that plane right there, right? Okay. So what would that mean? Well, that means that it's in the subspace, the orthogonal complement, right? Because if you then draw a plane that's that contains this blue line, it's a plane that cuts it at 90 degrees, right? if you guys try to visualize it, right? But how do we find the orthogonal complement of a subspace? Well, if you take the basis of of S, all you have to do is find the null space of the transpose of that matrix A, right? So in other words, um, B minus AX is in the null space of A transpose, right? So since, I guess you can say B minus AX is orthogonal, put this in, orthogonal to S, that means that B minus AX should be in the orthogonal complement. But we know that the orthogonal complement, so let's just say this, but S is equal to the null space of A transpose. So B minus AX is equal to, or is in the null space of A transpose. So what? Okay, so again, again, you guys, like, if you're lost, don't worry, we're almost there. You won't have to hear me talk about these things again. But if for conceptual understanding, what is a null space again? If let's say a vector is in the null space of a matrix A, what does that mean? Again, what was a null space in the beginning? How did we define it? It was a set of all vectors x such that ax equals 0, right? So here, so the null space of A is equal to the set of all x and whatever vector space you're in, such that ax is equal to 0, right? So if x is in this thing, then we know that A times that is going to be 0, right? Yeah, for sure. I was just trying to write this. So recall this. So if B minus AX is in the null space of A transpose, then what should we get when we multiply A transpose like this? 0, right? So here, so since B minus AX is in the null space of A transpose times B minus AX should be 0. Or in other words, we have A transpose B minus A transpose AX is equal to 0. Or in other words, we have A transpose AX is equal to A transpose B. And this thing, which is finally the punchline of all this entire thing, are called the normal equations. So basically, if you were to solve this equation for x, you find the best fit line or the best fit coefficients for your line. So if everything like I said was like going in one year and out the other, don't let this one come out of the other year, okay? So this one's the one that you know you need to know. Okay, so so now how do we use it? So we're gonna basically do that now. But again, the idea is we use all these properties of vector spaces, null spaces, column spaces, and we derived an equation. So this idea of deriving equations purely from structure is very big in math, especially if you're going to do even like higher stuff in like with like QFT and all that stuff. Like all this, I mean, this is like intro to that kind of stuff. Okay, so let's do an example to finish up for the day. So find a least square solution to say to the data well, guess what? So the data, what do we use in the beginning? We use this one. Okay, perfect. Yeah. So we're going to use this, basically this same example. 1, 0, 2, 1, and 3, 3. Okay. So we're going to find the best fit line for this. So again, solution. So again, we need to find our equations, right? So we need to find C1 and C2 for y equals C1 plus C2x. Plugging in points, we get the equation C1 plus C2 is equal to 0. C1 plus 2C2 is equal to 1. C1 plus 3C2 is equal to 3. In matrix form, we have 1, 1, 1, 1, 2, 3. We have C1, C2, and this is going to equal 0, 1, 3. So from here, what is A, by the way? A is that coefficient matrix, right? The 1, 1, 1, 2, 1, 3. So according to my thing over here, we need to solve this stuff right here. So take the transpose and multiply everything out. So here, let me just make this a bit smaller so everybody can finish, I guess, copying. So we need to solve A transpose A x is equal to A transpose B, right? So what is A transpose A? Well, if you take, this 1, 1, 2, 3 times 1, 1, 1, 1, 2, 3, and this is just going to give me the matrix 3, 6, 6, 14. Take A transpose B, which is going to be 1, 1, 1, 1, 2, 3, 0, 1, 3 is equal to 4, 1, 1. Okay, so now we have a new system, and we're going to use this to solve it. So we solve 3, 6, 6, 14 times C1, C2 is equal to 4, 11. If you do, using RREF or whatever you guys want to use, inverses, whatever you want, we get C1, C2 is equal to -5/3 and 3/2. So y equals -5/3 plus 3/2 x is the best fit line for that set of data that we originally proposed. Okay, so literally that's all you do. Is if I give you a set of data, get your equations, get your coefficient matrix, take the transpose, multiply it, and then solve this new system, and that's it. Like I said, if you got nothing else from today, just know that the normal equations are used to find the least square problem, or to solve the least square problem. Yeah, I'll go back. I'll send you this notes as well. Right after you guys are done. But yeah, but I mean that's pretty much. So that'd be the last thing. I won't, you know, ask like derive the normal equations or anything like crazy like that. However, I will do something like here's some set of points. Use the normal equations to solve for the least, for the best fit line or something like that. Okay. Okay. So let me export this. So anything that has normal equations, and that's it. Like it should, but I think, like I said, I think week 9 should be enough because I think we didn't go all the way to week 10 or whatever that the previous thing should have been. I think week 6 through week 9 should be enough for the extra credit. So. Because I don't think, yeah, because we haven't even gone through linear transformations yet, so. Okay, so let me get this to you guys here. And I'll give out a review. Week 6 through week 9. Okay, so I'm gonna have to email this out to you guys. So. All right. Well, I'll see you guys later.